Hi everyone, this is it, the final stretch before your IGCSE Physics Paper 4. Just bear this in mind. You have studied, you have practiced. Right now, you just need something that is powerful, something that is real quick, clear, and complete. So in this video, I am giving you the final boost to your IGCSE Physics Paper 4. I will recap every essential concept, the key definition, and must-know formula so that you can walk into that examination hall with confidence and clarity. So are you ready? Let us power up. So this is it. This is the final boost to your IGCSE Physics Paper 4. Right, I'm going through the topic one by one, tell you what are the important things, important concept, important keywords that you're supposed to write. When you enter your examination hall and you see the question, I pray hard that everything come clear to you. And let us get started. Now, first of all, this is about motion. Do you ever realize that when you try a lot of past year questions, there are surely, right, or most of the time, more than 90%, the question related to motion will be asked. So, right, these are the things that are very important, right? First of all, define speed. What is speed? I'm going to highlight the keywords. Speed is being defined as distance per time. And speed is a scalar quantity, remember? Because distance is a scalar quantity. Velocity is being defined as displacement per unit time. What is displacement again? Displacement is a direction, is a distance with a direction. North, south, east, forward, backward. This is displacement, right? Acceleration is being defined as rate of change of velocity. But if you don't want this definition, you can also define it almost similar meaning, right? As change in velocity per time taken. But you cannot put change in speed because speed is a scalar quantity. Acceleration is a vector quantity. So you have to put change in velocity. If you put change in speed, I'm very sorry. It's very hard to give you mark, right? Average speed is being defined as total distance travel per total time. So if you have three speeds given, for example, 10 meter per second, for example, 10 meter per second, 20 meter per second, or 5 meter per second. You cannot add up all these speeds and divide it by 3 and claim that's your average speed. Average speed is being calculated differently. So for 10 meter per second, if the time is being given, you have to find, let's say, for 10 seconds. So you have to find the distance traveled by the object within that 10 second. Maybe 20 meter per second, the time is only 5 seconds. 5 meter per second, the time is maybe 20 seconds. So you have to find the distance for every section. And then you just add out all the distances divided by the total time. That's your average speed. Now, graphs. Graphs are quite popular. In your syllabus, you only need to know about these two graphs. When a graph is being given, bear this in mind. Right. From the graph, you can obtain two information. One is the area under the graph. The other one is gradient. Only about area and gradient. Graph is only about area and gradient. Right. Bear in mind, if the distance time graph is being given, area represents nothing, but the gradient of the graph represents speed. If a speed time graph is being given, the area under the graph represents total distance traveled. Gradient of the graph represents acceleration. I would say that if you ask me to compare distance time graph and speed time graph, I will say that speed time graph is more popular. Why? Because you can obtain more information from the graph. You can find the area of the graph, you can find the gradient of the graph. But distance time graph, you can only focus on gradient. Now, wow, free fall. For free fall, you need to consider two situations. One is without air resistance. That means you conduct a free fall, right? You just drop an object, right, in space because there are no air resistance, right? So object without air resistance, all objects. If you conduct the experiment on Earth, right, will fall with gravitational acceleration. And if you assume that there is no air resistance acting on the object, then the gravitational acceleration on Earth is 9.8 meter per second squared. But if there is air resistance acting on the object, of course, you need to understand this. Air resistance increases as the speed of the object increases. So when the speed of the object is increasing, air resistance will also increase. And for every object that is falling, the speed is going to be increasing, not decreasing. Right, now let me explain on how the terminal velocity is reached. But before that, I need to explain the definition of terminal velocity. Terminal velocity is the maximum velocity when air resistance balances weight of the object. So when the terminal velocity is reached, there is no more acceleration because air resistance has already balanced the weight of the object. Acceleration, resultant force is equal to zero. Acceleration on the object is equal to zero. So the object will fall at terminal velocity, right? Constant speed until it reaches the ground. So when you are being asked with how the terminal velocity is reached, you can explain in terms of forces that are acting on the object or the acceleration. There is the variation of the acceleration on the object. So I will explain both just in case, right? So I am going to divide into three stages, right? I'm going to use different colors. So first stage, always start with at the start of the fall. Object is always at rest. Is that okay? So you must assume that the initial speed of the object is equal to zero, or initial velocity of the object is equal to zero. Initial, since they asked about terminal velocity, so I put initial velocity of object is zero. Remember what I wrote just now? Let us go back to my previous slide. I wrote that air resistance increases as the speed of the object increases. But at the start of the fall, since there is no velocity, there's no speed, air resistance is also equal to zero. Air resistance on object is zero. So the only force, if you talk about force, if you want to write about forces, the only force acts on object is its weight. Object, so due to the weight, object falls with gravitational acceleration. If you want to give more information, that is even better, of 9.8 meter per second square. That's it. That's the first stage. Okay, I'm going to use different color for the second stage. Right, second stage, once the object is falling, the speed is going to increase. When the velocity of the speed, velocity of object is increasing, air resistance acting on object increases. Air resistance is the resistive force that opposing the motion of the object. When the object is falling, object goes down, right? Object goes down, weight is acting downwards, but the air resistance try to push the object upwards, right? That makes the resultant force of the object decreases. Do you still remember how to find the resultant force? You take weight plus negative air resistance. Why I say plus negative air resistance? Because weight and air resistance are forces. Force is a vector quantity. So you have to consider direction. One, weight is acting downwards, air resistance is acting upwards. Right? Could you see that? So you have to plus a negative air resistance. That makes your resultant force acting on the object decreases. Right? So you just write here, resultant force acting on object decreases. When the resultant force decreases, what about acceleration? Of course, the acceleration is also decreasing because F mama, right? Acceleration on object decreases. And then after that, what happens? The last stage. Okay, last stage. When the velocity of the object, because the air resistance is going to increase until it can balance the weight of the object. When the velocity of object is maximum, air resistance increases to a magnitude equal to weight of object. So what happened? Because one outward force is balanced by the downward force, resultant force acting on object is zero, decreases to zero. So what happens to the acceleration? Acceleration on object decreases, is zero, sorry. So just write down zero will do because I have already explained decreasing. So is zero. And at that moment, object is falling with terminal velocity. Object falls with terminal velocity. So this is how you're supposed to explain. Let me highlight the keywords. If the question asks about forces and acceleration, I highlight both, okay? At the start, tell the examiner, before the object starts falling, initial velocity is equal to zero. So therefore, the air resistance must be equal to zero. The only force is weight, object falls, gravitational acceleration. Velocity increases, air resistance will also increase, resultant force decrease, air resistance decreases. Air resistance increases to equal to weight. Resultant force is equal to zero, acceleration is equal to zero, object falls with terminal velocity. These are all the important words, keywords, key points that you were supposed to write. Now, the next one, mass vs weight. State what is meant by mass. Mass is amount of substance contained in your body. Our body is made up of atoms. How many atoms in our body gives you your mass? Just take it like that, right? The unit of mass is kilogram, could be in gram as well. And apparatus, instrument to measure the mass, is called electronic balance. And bear in mind, mass is a scalar quantity. Scalar quantity means mass cannot take negative value, right? Weight, on the other hand, is being defined as gravitational force. acting on the body. So the unit of weight is Newton. Instrument to measure the weight is called Newton balance or Newton's meter or Newton spring balance. Weight is a vector quantity. Why vector quantity? Because the gravitational force acting on you, on me, on everybody here is directing towards the center of the earth. That is why weight is a vector quantity. Now, density. Density is being defined as mass per unit volume. So I have seen some of the past question ask you about how to determine the density of an object. So first of all, when you are asked to describe a simple experiment, always write down the apparatus. So what is the apparatus that we use to measure mass? Okay, just write down. It is electronic balance. What is the apparatus that we use to measure volume? So to measure volume, you have to look at the questions. Is the object, right? Does the object has a regular shape? What is the shape of the object? If the object is a cuboid, then you just multiply. You just use the ruler, measure the length, the height, the width. But if the object is irregular shape, you don't know what's the shape is that, then you have to look at the size of the object. If the size of the object is small, then you could use measuring cylinder. Right? I'm going to talk about that later. Okay, this is it. I'm going to talk about that later. So density, the definition is mass per unit volume. So formula, if you want to write down formula, it's not being given. Density, this is a symbol of density, it's called rho, m over v. M represents mass, v represents volume, rho represents density. And the unit of density could be in kilogram per meter cube because volume is measured in meter cube or gram per cm cube. Density, bear in mind, it is a scalar quantity. That's all. Now, how to calculate the density of an irregular shaped object? So maybe a small rock, right? So first thing, okay, you're supposed to prepare a measuring cylinder, but first thing, fill in water. Okay, into measuring cylinder. I measure the volume first. Oh, if you want to write the mass first, because when you see how to calculate the density, always write down the equation of density. Oh, density depends on mass and volume. It is okay. You can write down the mass first. Okay, mass is easier because we just place that object on top of the electronic balance. Place or use, okay, measure mass of object. Suggest the apparatus by using electronic balance. And after that, fill in water into measuring cylinder. Take its initial volume. And after that, carefully, or you can say place object into measuring cylinder. Take its final volume. And tell us, how do I calculate the volume of the object? So volume of object is equal to final volume minus initial volume. And last part, density of object can be calculated by mass of object. Maybe if you want to put a unit, just put gram, divided by volume of object. Because mass measured by electronic balance is in gram. Put cm cube. Is that okay? So I'm going to highlight the keywords right now. Measure mass, electronic balance, we want to see that. Fill in water, measuring cylinder, initial volume, I don't want to see that. And then volume of the object, final volume minus initial volume. And density, mass per volume. These are all the things that we want to see. The next one, Hooke's law, Robert Hooke. Do you still remember? Not Captain Hook. Hooke's law states that extension of an elastic material is always directly proportional to the force applied. 1 mark. Beneath the limit of proportionality. Now, what is limit of proportionality? Bear in mind, limit of proportionality is not equal to elastic limit. What is limit of proportionality? I'm going to write this down. Limit of proportionality means that, okay, maximum point in which Hooke's law is obeyed. But what is elastic limit? Elastic limit, it means maximum, okay, a point, okay, a point. Sorry, I just put a point. I just write this down here. Elastic limit. Elastic limit is a point in which exceeded, if you exceed that point, material undergoes deformation. What is deformation? That means changing of shape, changing of size, length will not return to its original shape or size or length. Is that okay? But Hooke's law is never about elastic limit. Hooke's law is only until limit of proportionality, right? So formula, I'm going to use red color. Formula F equals Kx. F represents force. K represents the spring constant. X represents extension, right? Graph, okay, you should know how to plot the graph as well. Since it is directly proportional, it could be extension against force or force against extension. Force slash the unit, extension could be in mm or cm. And the graph must always start from origin because when there's no force, there's no extension. So a straight line graph. Wow, we drew a graph. Remember what I told you? When the graph is being drawn, there are two information that you could obtain from the graph. One is the gradient of the graph. Let me write down. One is the gradient of the graph. Gradient of the graph, in this case, represents spring constant. Okay, this is called spring constant. So if you see a graph is being plotted, F against extension, bear in mind that's gradient of the graph represents spring constant. Area under the graph. Area represents work done in stretching, spring, or elastic material. Or you can call it as elastic potential energy. So there are two equations of elastic potential energy. One is, I put E represents energy, half Fx. You see, this is a straight line graph. If you find the area of the straight line graph, that will be the area of triangle. F represents force, X represents extension. If you don't want this, you can replace it with half Kx squared. Spring constant multiplies by extension, square it. So all these formula are very, very important. Yeah, and the Hooke's law is down. The statement of Hooke's law, you need to know how to state, right? And the graph itself, just in case they ask you to sketch, they ask you to plot, right? Remember, this is the graph. The next one, centripetal force. Bear in mind, centripetal force is not a new type of force, so you don't have to be terrified. It is just a normal force, maybe from friction, maybe from normal reaction force, etc. That causes object to travel in a circle. And the direction of the centripetal force, right? Always directed towards center of circle or center of the band. Sometimes they use the word band, right? And then centripetal force, I want you to bear in mind one more thing is that centripetal force acts perpendicular to motion of object. So in other words, like this. Okay. Let me draw, okay, a circle here. I'll draw a circle for you. You just imagine that this is a very nice circle. This object is moving in clockwise direction around the circle, right? So this is the direction of motion. Direction of motion is called the direction of the velocity. So if I want to find the direction of motion at this point, I put a cross here. I draw a tangent. This is the direction of motion, velocity. Centripetal force will act perpendicular. Can you see 90 degrees towards the center of the circle? This is centripetal force. That is why, since the centripetal force is acting perpendicular to the motion of the object or to the velocity, direction of velocity of the object, centripetal force does not change the speed of the object. It doesn't make the object move faster or slower. It is just responsible to change the direction of the object so that the object can complete a perfect circle, can travel around the circle. That's centripetal force. Now, turning effect of a force is called moment. You know, force can do many things. Force can make things move faster. Force can slow things down. And force can also cause a turning effect. The turning effect that caused by the force is called moment. So the definition of moment is the product of force and perpendicular distance from pivot. What is pivot? Pivot is a turning point. So if you want formula, definitely. Formula is equal to, okay, moment, formula. Moment equals to force. I always write it like this, multiplies by perpendicular distance. Right? Okay, the symbol of moment is T with a tail. We call it as tau, but it doesn't matter. It's just a symbol. Right? The unit of moment could be Newton meter, Newton cm, Newton mm. It is all depending on the perpendicular distance. Right? Bear in mind, moment, right, causes the object to turn. So moment itself is a vector quantity. So when the object object can only turn in two directions, right? Anti-clockwise direction or clockwise direction. Just look at the clock. Turn in this direction is called clockwise. Turn in this direction is called anti-clockwise. Now, principle of moment. You know, when in paper 4, sometimes they ask you to state two conditions for an object to be in equilibrium. One of it is this principle of moment. Principle of moment talks about what is the condition of the moment acting on the object in order for the object to be in equilibrium. So that is why I say for an object to be in equilibrium, total anti-clockwise moment must always be equal to total clockwise moment. So we use the principle of moment to form equation to solve problem related to moment, right? So you have to identify, do you know how to see what is clockwise moment, what is anti-clockwise moment? Let me show you, right? This is an object, for example, and this is a pivot. Sometimes it is called fulcrum. Don't worry, right? So let's say I have a force acting upwards here and a force acting downwards here. This is F1, this is F2, I call it, and this is F3, I call it. Is that okay? Now, I want you to see that, okay, this is a distance. I call it as distance 1. Okay, this is what we call perpendicular distance. You see, when the force is in vertical, perpendicular distance must occur in horizontal direction, x direction, because the force is acting in y direction. So x direction, this is called perpendicular distance 1 for force 1. This is perpendicular distance from the pivot itself. Perpendicular distance for F2. This is perpendicular distance of F3. Now, since We have all the perpendicular distances, and then we have all the forces here. I will highlight, okay, only 3 forces involved here. How do you determine which is clockwise, which is anti-clockwise direction? Now I want you to look at F1. F1 is going upwards, right? So because moment causes turning effect, so I want you to think it like this. F1 is going upwards. While going upwards, it will seek for where is the turning point? So it has to turn towards the turning point. So F1 moving outwards while turning to the turning point, this direction. What is this direction represents? This is called clockwise because you follow the direction of the clock. Right. Look at F2. F2 is going down. While going down, where's the pivot? It is on the right-hand side. So you have to turn to the right-hand side. So when F2 is turning towards the right-hand side, this is called anti-clockwise moment. What about F3? F3 going up. While going up, where's the pivot? Pivot is on the left, so we'll turn towards left. Turning towards left, this is also called anti-clockwise moment. Right? So if the whole system is in equilibrium, you have to look at it. So the question sometimes they don't mention equilibrium. The question would mention remain stationary. That means equilibrium, or remains horizontal. These are all the keywords for equilibrium. So I would say that this plank remains horizontal. So you can use anti-clockwise moment, principle of moment to solve. Is equal to clockwise moment. Just put everything anti-clockwise on left-hand side, which is F2 force times perpendicular distance x2 plus F3 force times perpendicular distance x3 is equal to F1 times x1. Ta-da! Then you just sub in the values that you have to find the unknown. Now, conditions for object to be in equilibrium. If a question regarding moment is coming up, normally the first part, they will ask you to list down 2 conditions for an object to be in equilibrium. Just memorize this. Resultant force acting on the object is equal to 0. What do I mean by resultant force? Let's say this is the object. That means the upward force of the object is balanced by the downward force. Forward force on the object is balanced by the backward force. Up is balanced by down, left is forward is balanced by backward. That is called resultant force. Resultant moment acting on the object must also be equal to 0. It means that the clockwise moment must always be equal to anti-clockwise moment. That's it. Next one, center of mass vs center of gravity. Remember, center of mass, it is regarding mass. Center, okay, I will highlight the keywords here. Center means a point. You have to write that. A point, center of mass, cm, which the whole mass is considered to act. Center of gravity is a point in which the whole weight of the object is considered to act. In your syllabus, IGCSE syllabus, we always assume that the center of mass is equal to the center of gravity when we do perform our calculation. It doesn't matter. But it comes to the definition, you have to put center of mass as a point which the whole mass is considered to act, whereas center of gravity is a point where the whole weight of the object is considered to act. The next one, momentum. We always say that if you want to be successful, you need to have a lot of momentum. Let us have a lot of momentum now. How about that, right? Momentum is being defined as a moving mass, right? As long as you are moving, you have mass, you have momentum. But if you are not moving, you're not progressing, you just sit down there procrastinating, then you have no momentum. Give a lot of momentum to physics. How about that, right? The definition of momentum is mass multiplies by velocity. If you want formula, definitely formula is equal to mv. And bear in mind, due to momentum is a vector quantity. Yeah, most of the students make a lot of careless mistake. I will show you later. So, and the unit of momentum is equal to kilogram meter per second or Newton meter. No, not Newton meter. Sorry, it's not Newton meter. It's a Newton second. Newton second. Why? I will explain later. Now, This has something to do with impulse. Impulse vs change in momentum. Impulse has two equations, right? Impulse can be calculated from two equations. One is force multiplies by time. The other one is change in momentum. So if the impulse is calculated using force multiplied by time, you can use the unit of kilogram meter per second, not a problem, or Newton second. Impulse represent change in momentum. So it is all depending on the question. If the question gives you force and time and asks you to find the impulse, just take force multiplies by time. If the question gives you momentum, initial velocity, and the mass, asks you to find the impulse, just put impulse as change in momentum, right? Final momentum minus initial momentum. Mv minus mu, that is also called impulse. M represents mass, V represents final velocity, and U represents initial velocity. So if you must know, how can impulse be equal to change in momentum? Let me prove it. Do you still remember force? F equal to mama? Yeah. And then the definition of acceleration, change in velocity per time taken, sub into the equation, you have m, v minus u over t, right? Times in the m, you have mv minus mu over t. Could you see that? So you times out cross multiplication, times out the t. So you have ft is equal to mv minus mu, which is equal to impulse. That is how we get. The next one, resultant force. Okay, resultant force is the sum of all the forces that are acting on one object. For example, this is the object. Object is moving, okay, push with 3 Newton. And there is also frictional force acting on the object, which is 1 Newton, right? Since force is a vector quantity, you have to consider positive and negative. You have to consider the direction. So if you want to consider forward as positive direction, then the backward will take negative direction. Just put negative. So resultant force, Fr normally, yeah, this is a symbol of resultant force. You can use this. 3 plus negative 1. So you get 2 Newton. That is how we find our resultant force. Now, work and energy. Work, the definition is the product of force and distance, but move in the direction of force. That also means that if I push you, I'm applying force on you, you have to move in my direction, which is forward. If I pull you, you have to move in my direction. So the distance calculated is in my direction of force. The unit of work is joules, remember, or capital J, and work is a scalar quantity. Energy, in general, energy means ability to do work, right? If you have ability to do work, then you have energy. So most of the time when we solve any question, right, regarding calculation, we always say energy is equal to work. Yeah, sometimes it is true, right? It is true in a way. Now, there are different energy that is very important in your IGCSE physics. One is gravitational potential energy, or in short, I call it as GPE. The definition of gravitational potential energy is the energy due to the position of the object measured from the ground. So you could see that, okay, when the object is on the ground, because there's no height, right? That is why the GPE is equal to 0. Let me put in the formula first. Formula of the gravitational potential energy is mgh. M represents mass. G represents gravitational. Acceleration. The value is 9.81 meter per second square. H represents height from ground. And when the object is on the ground, there's no height, so that is why GPE is equal to 0. But whenever object is being lifted out to a certain height, let's say this is a height, h, then the object will gain GPE. How do you calculate the GPE? By using the equation that I gave you. And the unit of GPE is still joules, which is equal to work. In fact, all the energies are measured in joules. Mass must be measured, let me tell you this. Mass must be measured in kilogram. H must be in meter in order for you to get joules. No, most of the time, some tricky question, they give you the mass in gram. Bear in mind, just convert to kilogram. That will do, right? And the gravitational potential energy is also a scalar quantity. Yeah, that is all about gravitational potential energy. The next one is the kinetic energy. It's the energy due to motion, or in short, I call it as KE. So as long as you're moving, as long as the object is moving, object has mass, and it is moving, object has kinetic energy. Formula, KE is equal to half mv squared, where this m represents mass and v represents the speed, but you have to square it, right? And the unit is joules. Mass must be in kilogram, speed must be in meter per second. Just square it, meter square per second square. And kinetic energy is also a scalar quantity. That's all. Principle of conservation of energy. Normally they will give you 2 marks. So states that energy cannot be created nor destroyed. That's 1 mark, but can change from one form to the other form. That's all. So we can also use the principle of conservation of energy to solve equations. So you just need to remember, okay, first one, when resistive forces like frictional force, air resistance, okay, are ignored. Then you can use the principle of conservation of energy to solve it. That means you just write down total initial energy is equal to total final energy. Total initial energy could be kinetic energy, could be gravitational potential energy. It depends on the questions, right? The second condition is when resistive forces are not being ignored. What happened? So you have to do a little bit of modification to your principle of conservation of energy. You just write down total initial energy minus, okay, energy dissipated, or work done in overcoming the resistive force, right? To overcome resistive forces, then only equal to your total final energy. Remember. Now, efficiency, right? You know why we calculate efficiency? There's not a formula here. It's just ratio. We calculate efficiency because we want to see our motor, right? The output given out by the motor. Is it the one that we expected? How much different? I put in this amount of energy. How much energy that I should get in the end? That's efficiency. The larger the value of efficiency, the better, yeah, the machine or the motor is, right? The equation you can use efficiency is always equal to the useful output energy per input energy times 100%. So the efficiency, the unit of efficiency is in percentage if you times 100%. But if you don't times 100%, then your efficiency is in the form of a ratio. But bear in mind, in physics, we don't leave our answer in fraction. We put it in terms of 2 to 3 significant figures only. Or efficiency can also be calculated by, if you don't want to use, if the useful output power is not giving, useful energy is not being given, you can use useful output work over input work times 100%. If you are not given work, doesn't matter, just use efficiency equal useful output power over input power multiplies by 100%. Okay? Now, power. Show that you have the power. This is a symbol of power, capital P. Power is defined as work done per unit time or energy per unit time. So the equation of the power formula, power is equal to energy over time, or power is equal to work done over time, right? The unit of power is watt. What? Yes, watt is the unit of power, and power is a scalar quantity. Let me write down. Okay, this is called energy. This is the time, and this is the work done. This is the time. Now, pressure. Don't give yourself too much of the pressure. I know IGCSE physics is no joke, but don't give yourself too much of the pressure. Relax, right? The definition of pressure, right, is defined as, don't ever define pressure as density times g times gravitational acceleration times the height. No, no, no. Pressure, one physical quantity, one definition. And the definition of pressure is force per unit surface area. If you are asked to find the pressure of the solid, then we always use this, okay, for this formula. P is equal to F over A. F represents force, A represents surface area, P represents pressure. And the unit of pressure could be in Pascal only when force is in Newton, area is in meter square. But, okay, therefore, you can put unit of pressure as Newton per meter square as Pascal, or Pascal is equal to Newton per meter square, same unit, or Newton per cm square, Newton per mm square, depending on the area, surface area. Pressure of fluid. You know, fluids are gas and liquid. So if they give you the density of the fluid, then the pressure formula is equal to P equals to rho GH. Let me explain. P is the pressure, rho is the density of the gas or the liquid, G is the gravitational acceleration. H, okay, for liquid, H is the depth, but for gas, H is the height, depth. Okay, the depth of the liquid must be measured from the surface of the liquid downwards to where the liquid is, not outwards, because outwards is gas from the surface of the liquid. Right. Internal energy. So in IGCSE syllabus, you need to know the definition of internal energy, not the equation. Don't worry. So internal energy is the energy inside an object, right? So let's say you have a glass of water, right? There are particles inside the water, liquid molecules, and these liquid molecules, they are moving, right? Even though it's restricted. And they're moving, they have kinetic energy. And due to the distance between them, they have potential energy as well. That is why internal energy is being defined as the sum, the total sum of kinetic energy and potential energy of the random moving particles. Whether you're talking about solid, no random, you're talking about liquid, no random, but as long as they are moving, or gas, random moving particles. Now, this is how the thermal energy is being transferred, right? Conduction, convection, and radiation. Bear in mind, conduction, one more thing. Before we look into conduction, convection, and radiation, bear in mind, heat can only be transferred when there is a difference between the two objects' temperature. Whenever there's a temperature difference, if the surrounding and the object has the same temperature, then heat cannot be transferred. Heat is equivalent to thermal energy. When I say heat, it means thermal energy. Thermal energy can only be transferred when the temperature different, okay, between two objects or object with the surrounding. But if the temperatures of the two objects are the same, then no heat is being transferred. First one, this is how the heat can be transferred. Conduction. Conduction is the transfer of heat from the hotter end to the colder end in the solid. Let's say um you are giving one end. This is a metal, and then you place a fire here. This is a fire, and then you just hold the other end. Since this is a metal will transfer heat from the vibrating atoms and the localized electrons to the other end. Heat must be transferred from the hotter end to the other end. So when you touch the other end, you could feel hot. Ouch, like that. That is conduction, right? There must be physical contact between you and the other object. Okay, there is this one is a clue, just a tip. There is physical contact between two objects. How about that? Convection, on the other hand, is not valid to solid. Okay, not valid to solid. Remember why? Because convection is the circulation of heat from the hotter region to the colder region. So the particles must move in order for the heat to be circulated. Right? So about convection a little bit. Hotter. Okay? Particles, okay, have larger kinetic energy, right? Or they expand, volume increases, right? So density decreases. That is why when you heat up a place, okay, air particle inside the room, the hot air will rise, right? Same goes to liquid molecules. Whenever you heat this out, you put fire here. So these liquid molecules that gets the fire first, gets the heat first, they get heated out. So the liquid molecules will expand, which makes their distance further away from each other. So density, back to density, mass over volume. So when the volume decreases, the density will when the volume increases, the density will decrease. That is why the hotter molecules will rise out and the colder particles. Why I put red color for the colder particles? I hope I don't confuse you, yeah? Have smaller Ke. So smaller volume, right? Because the particles are closer, because they are colder. They don't have enough energy to expand, right? Density is larger. So that is why the colder particles will move down, out. Hotter particle move out, circulation of heat occur. Okay, radiation is the transfer of heat from the hot region to the colder region without physical contact. For example, every morning you wake up, okay, when you see the sun, you can feel the heat from the sun. But bear in mind, between the earth and the sun, there's nothing, it's just a vacuum. This is called radiation. Or you go for a campfire camping. So nighttime you set up campfire. So it's just because you are cold, you sit close to the campfire. Are you touching the campfire? No, right? But you sit close to the campfire, you can feel the heat. So you feel warm, you feel more comfortable. This is radiation. Now, boiling vs evaporation. Boiling is the changing of phase. I'll highlight the keywords. Changing of phase from liquid to gas at fixed temperature. Evaporation, the definition is changing of phase from liquid to gas as well at any temperatures. Remember, boiling, occurs at boiling point. Since I already write fixed temperature, I will replace this with boiling point. Evaporation occurs at any temperatures, yeah? Temperatures, remember. And then boiling occurs throughout the whole liquid. But evaporation only occurs at the surface of liquid. That's it. Specific heat capacity. Okay. If you see this word specific heat capacity, the first formula, I talk about formula first. Formula. If you don't remember the definition, it doesn't matter. First thing, you see the word specific heat capacity, straight away put E equals mc delta T. Because to calculate the specific heat capacity, there's only one formula, which is the one that I stated here. E represents energy or heat, right? Thermal energy or heat, energy or heat. M represents mass, must be in kilogram as energy is in joules. C represents specific heat capacity, symbol is C. Delta T represents change in temperature. Could be in degrees Celsius, could be in Kelvin, doesn't matter. So if you cannot memorize the definition for the specific heat capacity, doesn't matter, you can use equation. So you can put C is equal to E over M delta T. But don't just leave it like that, put a comma. Where C is the specific heat capacity, E is the thermal energy, M is the mass, and delta T is the change in temperature. That's all that you need to write. Remember that. So if you can remember the definition, just check whether you still remember, whether you get the correct definition. So it is a heat supply or thermal energy supply per unit mass to increase its temperature by 1 Kelvin or 1 degree Celsius. Doesn't matter, right? Now, but you have to remember mass must be in kilogram because the energy is in joules. Sometimes the question is too tricky, right? Because in physics lab, we don't have Bunsen burner. So there is no apparatus to calculate the thermal energy. So normally in physics lab, we use heater. Heater comes with power rating, right? But don't worry, don't get panic. When the power is being given and we use a stopwatch to time the time to heat out the object, right? So how much time that I use to heat out this substance, right? So how to find the energy? Thermal energy can be calculated if you recall. Oh, power is equal to energy over time. Yes, exactly. So you could replace the energy, equation of the energy as power times time equal to mc delta T. Just in case if they don't give you the heat or the thermal energy, you can use power. If they give you power, this is the time. So the unit of specific heat capacity is joule per kilogram per degree Celsius, right? Joule per, wait, let me see. Joule per kilogram per degree Celsius, yes. Or joule per kilogram per Kelvin. It depends on the temperature. Now, waves. There are two types of waves that you have to memorize. One is transverse wave. The other one is longitudinal wave. Transverse wave, okay, I will highlight the keywords. Transverse wave means that weakest waves means vibration. Vibration of what? Vibration of the particle, which is for transverse, perpendicular to the direction of travel of the wave or the direction of propagation of the wave. Doesn't matter. Longitudinal wave, you have to talk about vibration. But vibration of what? Vibration of particle, which is parallel to the direction of travel of the wave. Right, this is how I remember. Transverse, give you some tip, put 90 degrees. You don't like to put the word perpendicular, just put 90 degrees, what's wrong? Or you can put right angles, not a problem. For longitudinal wave, I just put A in front. Along. So you don't want to put parallel? Just put along. Vibration of the particles is along the direction of travel of the wave. Right? So the examples of the transverse wave is light wave, water wave, radio wave, microwave, etc. Longitudinal wave, example, sound wave, okay, ultrasound. Yeah. So something related to sound. That is called longitudinal wave. So I prefer you to memorize longitudinal wave because less example. So other than sound, right, everything are transverse wave. General equation of the wave, V is equal to F lambda. V is called wave speed. F is called the frequency of the wave. And lambda is called the wavelength of the wave. Now, wavelength, right? Sometimes they give you a graph. Remember, when the graph is being given, check the x-axis on the graph. If the x-axis is distance, right? So the wavelength, you can safely use this graph. Wavelength is one complete the length of the wave, okay? How fat the wave is, that's called wavelength, right? Wavelength is being defined as distance between two successive crests or two successive trough. Crest and trough, right? Or you start from origin back to origin. Frequency, on the other hand, when the graph is being given, right? Frequency can be calculated. When the graph is being given, check your x-axis. If your x-axis is time, then you determine not frequency, but period first, right? This is called period. Period is the time taken for one complete oscillation. So frequency can be calculated by 1 over period. T means period. Done. Now, this is a phenomenon, one of the phenomenon of wave reflection. Reflection means the change in the direction of propagation of wave when it strikes a reflecting surface. So you need to have a reflecting surface. Okay, let me draw it nicely again. Okay, you need to have a reflecting surface. Okay, this is called reflecting surface in order for the reflection to occur. And then on the reflecting surface, you need to draw a dotted line which is perpendicular to the reflecting surface. This line is called normal. What is normal? Normal is an imaginary line which acts perpendicular to reflecting surface. Okay, and then check. Okay, this is the light ray that is coming. You have to put arrow, right? Light ray is striking on the reflecting surface. This ray, if this is a light, then this is called light ray. But if this is just a wave, then you say this is incident wave. And then wave that is directed away from the reflecting surface is called reflected wave. Okay, the angle between normal and incident, that is why normal is very important. The angle between the normal and the incident wave is called incident angle. Incident angle. The angle between normal and reflected wave is called reflected angle. So reflection, the law of reflection, bear this in mind, angle of incident must always be equal to the angle of reflection. So if the angle of incident is 50, angle of reflection must be 50 as well. That's all. Refraction. Okay, the keyword is that bending of wave. When a wave travels through different media, maybe from air to glass, glass to air. Why wave ever bend? It is because the speed of wave is different due to the different densities of different media. So one thing that you should know, two things, right? You should memorize. One is this one. Let's say this is air, this is water, this is also air, this is normal, okay, this is water. So if the wave is coming from air to water, it will be bent, refracted towards normal, right? Okay, when wave travels from less less dense is your air, to denser medium, which is water, wave refracted towards normal. So in other words, I can say that incident angle, refracted angle. Refracted angle is smaller than the incident angle. But if the wave travel from denser medium to less dense medium, then the wave will be refracted away from normal. So I'm going to write that. This is called incident angle. This is called refracted angle. So when wave travels from denser medium to less dense medium, wave refracted away from normal. Remember, normal is very important. So you need to draw towards normal, away from normal. Less dense to denser, denser to less dense. Remember that, memorize this, okay? Now, refractive index or the symbol is small letter n. Do you know why we calculate refractive index? Just to see how much bending has already occurred when the wave travels from one medium to the other medium. So there are different equations and can be calculated from sine I over sine R. I is the incident angle, R is the refracted angle. And also can be equal to sine R over sine I. And also can be equal to the speed. I don't want to write speed of light. Speed of light in vacuum or speed of light in air, yeah? Which is 3 times 10 to the power 8 divided by speed of light in medium. Okay, and N also can be calculated from the real depth. Okay, I will explain this over apparent depth. Real depth meaning to say that you go to the swimming pool. If you're standing at the middle of the swimming pool, I'm outside from the swimming pool, I could see your legs are getting shorter. Why? Because the bending of light, it seems that your legs will be shorter. Or you go to a crystal clear river, you can see all the fish swimming. You could say that, hey, how come the fish, you try to catch the fish with your bare hand, right? Most of the time you cannot get. Why? Because the fish appear to be close to the surface of water, but when you try to catch them, right? Because they swim in the school, right? A lot of them, that's why we call them as school of fish, right? But the real depth, right? The real location or the position of the fish is deep down in the water. Right, now let me tell you when to use sine I over sine R. This is valid when the wave travels from denser, no, less dense, less dense medium to denser medium. Sine R over sine I when the wave travels from denser medium to less dense medium. Okay, you might look at all the equations that I stated for refractive index and you get demotivated. But don't get demotivated. You know why? I have a very important tip to share with you. You know, I love shortcut. I want to share my shortcut with you. So if you can't remember, because I'm not good in memorizing stuff as well, if you can't remember, it doesn't matter. I have just put this aside. You know why? Whenever you calculate, let's say you get sine I over sine R or sine R over sine I, it doesn't matter if you're confused, right? Let's say you sub in wrongly. Let's say this situation occur. Here, this one is 20 degrees, for example. This one is 50 degrees, right? So you use refractive index of the water and is equal to sine, is it sine R? I wonder. So you just put sine R over sine I, right? Sine R is 20, I is 50. Okay, use your calculator. Where's my calculator? Use your calculator. Just put sine 20 divided by sine 50. Okay, you get a value, which is 0.446, right? Refractive index has no unit. So when you get a value of 0.446, you have to know right away you are doing wrong thing. Why? One tip that I want to give here, refractive index that you calculated must be more or equal to 1. If you get lesser than 1, like what I did here, I get lesser than 1. No worries. Okay, just cross, redo. N is equal to sine 50 over sine 20. Okay, let us do sine 50 divided by sine 20. And I got 2.2. Yes, it is more than 1. As long as the refractive index that you calculated is more than 1, yes, that's correct. Okay, that's the tip. Diffraction. Diffraction means spreading of wave. When a wave travels through a small aperture, travel through a small opening, yeah, or block, etc. Right. I want you to bear in mind when diffraction occur. right? Did I give you? Okay, I will give you one more slide, which I'm going to draw it out. When diffraction occur, okay, no change in wavelength. I will explain later. No change in frequency of the wave. Frequency remain constant after being diffracted. No change in speed of the wave. Why? Because V equal to F lambda. Since the frequency is constant, the wavelength is constant, then the wave speed is also constant. But, okay, what is changing? Direction of wave changes. So due to the, why? Direction of wave changes because wave, when passed through the small opening aperture, it will spread out. Spreading, that means move outwards in all direction. So since the wave's direction changes, you bear this in mind. Velocity changes. Velocity of the wave changes. Okay, because velocity depends on direction. Yeah, now I'm going to draw you the wave. This is, let's say this is small opening. This is the larger opening. Okay, now normally they would draw you, okay, wave front. They would draw you wave like this. Okay, the distance, this is called wave front. Distance between one wave front to the other wave front is called wavelength. So whenever you see this question, use your ruler, okay, or you see with your naked eyes, right? So if you see that the wavelength is almost similar to the size of the gap, this is the size of the gap. I put it as A. So if the wavelength value is almost similar to the size of the gap, then bear in mind maximum diffraction occurs. Is that okay? Maximum spreading occurs. Right? This is how you're supposed to draw it. I'm using green color. So a lot of pushing spread out, right? The wave is more circular. And then try using your naked eyes again. Draw back, but make sure that the gap between the circle, okay, or circular wave is almost similar, constant, because wavelength cannot change after being diffracted. And then don't just stop there because you need to draw arrows to show that the wave is being spread out after passing through the gap. So when the gap is bigger, which is larger than the wavelength, this is wavelength, right? Size of the gap is large, not much of the spreading occur. So not much of the spreading occur, it will just curve at the edges. Wavelength remain constant, like this. And then just draw arrows to show that the wave is being diffracted, spread out. So normally drawing diffraction for the wave, they will give you 5 marks. 1 mark each for the pattern of the wave. So you draw 2 waves, two different types of patterns. And then 1 mark will be given for the first wave when the lambda is constant. Wavelength is constant. And then for the second wave, wavelength is constant as well. 4 marks already. And the 5th mark is going to give to the direction that you show that the wave is being spread out after being diffracted. Right? Remember. Now, critical angles and total internal reflection, right? Critical angle, the definition is refraction of the light wave. Normally, we use simple experiment, we use light so that we can see. Refraction of light at 90 degrees on the surface when the light travels from denser medium to less dense medium. Total internal reflection is the phenomenon which the light ray is being reflected inside the denser medium when the light ray is incident from, okay, or the incident angle of the light ray is larger than the critical angle, yeah, of the denser medium, and the light must be traveling from the denser medium. Okay, let me explain. In order to get your total internal reflection, right, you have to fulfill this condition. First one, the light must travel from denser medium to less dense medium. Water to air, glass to air, right? And the angle of incident of the light ray must be larger than the critical angle of the medium. So, okay, before that, let me discuss a little bit about the simple experiment to determine the critical angle. and to prove total internal reflection. Okay, let us discuss a simple experiment for total internal reflection, right? So discuss, this is the title, discuss a simple experiment for total internal reflection. Now I want you to see this. Let's say this is a water, this is air, this is water, this is normal. And then I need to have a laser box because I want to direct the light. So the laser box must be wrapped up nicely because you place it in the water. So you direct, laser box will give out light. Why we use laser? Because laser light is the illumination or the intensity of the laser light is stronger, so we can see the result, right? I don't know the critical angle of the water. So I start with a small angle. So that is why, okay, I make sure that my laser box start at small angle. Okay, direct light onto, okay, the air. So let's say angle incident, yeah, angle of incident is smaller than the critical angle. What happens? You could see two rays only occur when the angle of incident of light is smaller than the critical angle of the water. You could see two rays. One, refraction of the ray. The other one, a fainter ray being reflected into water. So you can see two rays. But if you increase, let's say you keep on increasing the angle of incident, I just ignore that laser box. Is that okay? So I just draw you the angle of incident. It increases because I want to determine the critical angle first, right? If the incident angle is equal to the critical angle, this is air, this is water, right? This is what you will see. Oh, the light ray, very nice, because I conducted the experiment. The light ray will be refracted at the surface of the water. It's so nice. This is called 90 degrees. And then when you keep on increasing, yeah, the angle of incident, right, which is larger than the critical angle incident, which is larger than the critical angle, all the light ray will be reflected into the water. No light ray is refracted into the air. So this is the condition where the total internal reflection has already occurred. Now I would make my explanation. When incident angle is smaller than critical angle of water, some of the ray is refracted, some of the ray is reflected into water. Second, okay, when incident angle is equal to critical angle of water, ray will be refracted at the surface or interface of water and air. Or you say 90 degrees, not a problem. And then the last point, when incident angle is greater, I'll highlight the keywords later, than critical angle of water, all the rays are reflected into water. So we could say that total internal reflection occurs. Okay, now the keywords are incident angle, smaller, critical angle. I want to see refracted, I want to see reflected. Incident angle equal to the critical angle refracted at 90 degrees or interface. Incident angle greater than the critical angle, I want to see reflected into denser medium. Total internal reflection has already occurred. That's all. Now, okay, definition of some terms. Yeah, for your lens, converging lens, bear in mind focal length. Length means distance. Distance between focal point and the center of the lens. Distance, focal point and the center of the lens. Focal point is a point. Okay, sometimes it is called principal focus. It is the point in which all the rays would be refracted to after passing through converging lens. Principal axis, on the other hand, is just an imaginary horizontal line that you draw, right, passing through the center of the lens. So all the measurements, whether the image is getting larger or smaller, image is inverted or upright, is depending on, based on principal axis. Right, let us see. Ray diagrams for converging lens. There are three rules that you have to understand. So the first rule is that any ray that is parallel to principal axis will be refracted towards focal point or principal focus. Right? So this is your lens, for example. Okay, this is what we call principal focus. Cut through the center of the lens. So since the lens has two curvature, so there are two focal point. Any ray that is parallel, this is the center of the lens, parallel to the principal axis, the horizontal line will be refracted at principal focus. And whenever you draw a ray diagram, put arrows. Right. And the second point, any ray that passes through center of lens will go through straight. No refraction occur. So I draw like this. I draw a smaller one. Principal axis is here, right? And then these are all your principal focuses, right? If the ray passing through the center of the lens, it would just go through straight like this. Is that okay? And the third one, any ray that passes through principal, I just write focal point. Is that okay? Focal point first, pass, because there are two focal points, right? Pass through the first focal point before the lens. Pass through focal point will be refracted parallel to principal axis. Okay, I'm going to draw that out like this. Okay, like this, center of the lens. Just imagine that this is a very nicely drawn center of the lens, and then these are the two focal points. Pass through the first focal point, go through straight towards the center. You can extrapolate the graph here. Just draw a straight line, will be refracted horizontally. These are the three rays that you have to remember. Three rules to draw the ray diagram for converging lens. Now, ta-da! Could you see ray number one? Any ray that is parallel to the principal axis will be refracted towards focal point. Right? Any ray that passes through the center of the lens just goes through straight, and any ray that passes through the principal focus first or the focal point first will be refracted horizontally. Right? So the intersection between these three rays will give you the location of the image. So the characteristic of this image, okay, let me talk about characteristic. Yeah? This image is real. Why it is real image? Okay, the part, okay, the curve which the object is facing is called the front part of the lens. So the other side of the lens is called the back of the lens. So whenever the image is being formed at the back of the lens, the image is real. And okay, like what I say, this is our principal axis. Could you see that from an object going upwards? So from the principal axis, where's the image? Image is formed below the principal axis. That is why the image is called inverted, because object is formed at the top, right? On top of the principal axis. And clearly, when you measure the height of the object and compare with the height of the image is diminished or getting smaller. The opposite to diminish is enlarge. Opposite to inverted is called upright. Upright. If the image is formed up here, then you can call it as upright. The image of real is virtual. Image is virtual when the image is formed on the same side as the object. Somewhere here. That's virtual. Now, dispersion, right? Dispersion is the spreading of light into white light into 7 colors when white light passes through a prism. So you use a prism to spread the white light into rainbow. That's dispersion. Now, electromagnetic spectrum. So you have to memorize the sequence. Whether you memorize in terms of increasing frequency or increasing wavelength is totally up to you. Bear in mind, all the electromagnetic wave travels with the speed of light in air and vacuum. So I memorize it in terms of increasing frequency. So I'm going to write down here. First one is radio wave, microwave, infrared, visible light, 7 colors, ultraviolet, X-rays, and gamma ray, right? So this is in terms of increasing frequency. Okay, of course, not just memorize in terms of increasing frequency. You need to know their function as well. What are the usefulness of this electromagnetic spectrum? Radio wave, right? It is used in radio station, broadcasting, radio station. Radio station, you listen to the radio. Yeah, it is actually from the radio wave, right? And then you could also use microwave. It is being used for cooking. Oh, sorry, radio wave. Okay, cell phone, radio station. Microwave is for cooking, and then satellite communication. Do you know what is satellite communication? Let's say you want to watch football, right? Football that happened in some of the country. You want to watch live, right? You can, but you just need to tune your time, right? So this is called satellite communication because it allows, due to the microwave, you're allowed to watch live show without flying to that country. So this is satellite communication. We use microwave. Remember that. Infrared is being used in the TV remote control. So when you press the TV remote control, you can see red light, that's infrared. Or you can use in toys remote control. Visible light, maybe traffic light, the light that you can see. Red, green, yellow. Ultraviolet, sterilization of the medical equipment. X-ray, used for X-ray. Gamma ray is used for cancer treatment. Now, loudness vs pitch. This is related to sound wave. Loudness is related to amplitude. Pitch is related to frequency. So amplitude increases, loudness increases, and vice versa. Pitch increases, that means frequency increases, pitch increases, and vice versa. I draw a graph. So if you compare, right? Okay, this is displacement. Y-axis is always displacement. X-axis could be time, right? Could be distance, doesn't matter. So I want you to compare the black wave that I'm going to draw. Compare with yellow wave. See this? So I will say that yellow wave has lower, okay, or it is softer because the yellow wave has lower amplitude. Amplitude, you look at the y-axis. Pitch, on the other hand, okay, you compare green wave. Pitch, the x-axis must be time. Green wave, okay, amplitude is the same, yeah? Okay. And then the other wave is maybe blue wave. Can you see? Blue wave has a higher pitch. Why? Because frequency is being defined as number of wave that form in 1 second. Number of complete oscillations in 1 second. That is frequency. If you can form more number of waves, that means the frequency is higher. So the blue wave has a higher pitch. That's how you see. Right? Echo, remember, echo is the reflection of sound wave. Formula, V is equal to 2 times the distance divided by time. V is the wave speed, sound wave speed. Okay, D is distance, and T is the time. Bear in mind why I put 2 times the distance. Memorize this because the sound wave must travel to and be reflected back to you in order for you to listen to echo. That is why 2 times the distance. Now, move to electricity, the definition of electric charge, yeah, charge. Definition is equal to the product of current and time. Formula, Q8. This I remember, Q8. Q is the charge, I is the current, T is the time. Yeah, unit, coulomb, or capital C. Charge, okay, 2 charges, positive and negative. Bear in mind, only negative charge can move. Only electron can move. Right? Current, okay, cancel. Current. Definition of current is rate of flow of charge. Same thing. Okay, I'm using different color. Current is equal to charge over time. Unit, ampere or capital A. And bear in mind, current flows from positive terminal to negative. Whereas electrons on a negative charge, electron flows from negative to positive. Remember that. DC vs AC. DC is called direct current. So the definition of direct current is the current that flows in one direction only. Graph, I have 2 graphs here. So you can see that, okay, this is current, this is time. Current and this is time. So the graph could be all the currents are positive or all the currents are negative. This is called DC. DC, yes, direct current. AC, on the other hand, is called alternating current. Alternating current is the current that reverses its direction every half a cycle. Graph, only one graph I have, right? This is time, this is the current. So the graph, up and down. Sometimes you get positive value of the current, sometimes you get negative value of the current. So this is called AC. Now, electromotive force or EMF, Vs, potential difference or PD. EMF, right, is defined as energy supplied per unit charge in moving the charge through a complete circuit. So equation, formula. Yes, formula. EMF is equal to energy per charge. Unit, volt. Okay, and the sources of EMF. Let me give you power supply, battery, cell, etc. PD, the definition is work done per unit charge in moving the charge from one point to another. This is called PD. And formula, PD, or normally we put V. V is equal to work over charge. Unit is the same, volt or capital V. Sources of PD could be resistor, lamp, LDR, light dependent resistor, thermistor, etc. Now, Ohm's law states that current is directly proportional to potential difference, one mark, when the temperature of the conductor is constant. If the temperature is not constant, Ohm's law is no longer valid. Is that okay? So graph, whether you plot IV graph or VI graph, it doesn't matter. So as long as VI is ampere, start from origin, it is a straight line graph. Okay, from the graph, I remember I told you when the graph is being given, you can find two information. One is the gradient, the other one is the area under the graph, but not valid to Ohm's law. Remember, Ohm's law, resistance, right? Resistance is not the gradient of the graph. You have to delete that right away. Resistance is the ratio of potential difference to current. Remember, never gradient, don't ever find gradient. So you find gradient is the same as the ratio for a straight line graph. But what if the graph is not straight, but the graph is curved, like the graph of filament lamp? So you have to bear in mind, ratio. Just see the value of potential difference, get the value of the current, and then just divide. That would do for resistance. Yeah. So Ohm's law formula, V equals to IR, where V represents potential difference, PD, I represents current, and R represents resistance. Unit of resistance is ohm. Unit of current is ampere, unit of PD is V. That is Ohm's law. Now, electrical energy. So I split into two parts in order to make your life easier for your calculation. So if you see energy supply, normally this is the equation that we use. E equals to VIT. Energy loss, normally we use E equal to I square RT or E equal to V square over R times T. It doesn't matter which equation you use. Make sure that you get enough information before you use, if you have enough information, you can use the first one. If you have lack of information, maybe you should consider to use the second or the third one. E represents energy, V represents PD, I represents current, T represents time. Time must be in second. Current ampere, PD is in volt. Energy must be in joules. Remember, all kinds of energies, they are measured in joules, right? I, current. R represents resistance, must be in ohm. Time, second. Right? Just memorize this equation. They're not being given. Power, on the other hand, you can use P equal to IV. Or power loss, P equal to I square R, or P equal to V square over R. So I represent current like usual. P represents power. Power must be measured in watt. V represents PD, must be in volt. Current ampere, power is watt. R is called resistance. Resistance must be in ohm. That's all. Now, thermistor. Thermistor, this is a symbol of thermistor. Okay, so what is the function of the thermistor? Working principle, yeah? Thermistor depends, thermistor depends on temperature. So when temperature increases, resistance of thermistor decreases. Opposite. Let me write that down. Decreases. When temperature decreases, resistance of thermistor increases. Right? Graph. When you draw resistance against the temperature or the temperature against resistance, it doesn't matter. Okay, inversely proportional. Right, highlight the keywords. Temperature increase, resistance decrease. Temperature decrease, resistance will increase. That's all. LDR stands for light dependent resistor. So symbol. So arrow to show that the light hits it. So it is made of semiconductor, cadmium sulfide normally. So the working principle, when light intensity means brightness. Intensity is high. Resistance of LDR is low. When light intensity is low, resistance of LDR is high. Graph. Resistance against intensity, inversely proportional. Okay, so I'm highlighting the keywords. Intensity is high, resistance low. Intensity low, resistance high. That's all. Series circuit. Series circuit, you have to imagine that we are so happy we are holding hands side by side. Series circuit is like this. Resistor 1, resistor 2, resistor 3. They are side by side. Current has only one path to flow, right? This is a total potential difference, total voltage. Voltage 1 across resistor 1, V2 across resistor 2, and V3 across resistor 3. So bear in mind, in series, I use red color, current is the same. Okay? I is equal to the same I that flowing through R1 is the same current that flowing through R2 is the same current that flowing through R3, right? But the total potential difference, total voltage or the EMF is equal to the sum of all the PDs across the resistor. So using Ohm's law, V equal to IR. So V total is equal to IR total, IR1 plus IR2 plus IR3. Now my favorite part is here. Cancel all the I. You left behind R total is equal to R1 plus R2 plus R3. Could you see that? When all the resistors are connected in series, you just sum up all their resistances. So the total resistance will increase. Parallel circuit. Okay, I need to draw that. Parallel circuit is like this. Okay, go behind each other. Okay, R1, R2, and R3. So you see, I want you to see this. This is a junction coming out. This is a current total. Junction, current will split to, okay, different branches here. Junction is like you are driving in a car. So junction is where the car splits. Some of the car will go to the right, some of the cars will go to the left. Right? Same goes to this circuit. Bear in mind, EMF, okay, is the same as PDs. Yeah? So the EMF is constant. Now, I'm going to prove that. So since the total current, yeah, total current, I total is equal to I1 plus I2 plus I3. So you use Ohm's law. I is equal to V over R. So that is why you get V over R total is equal to V over R1 is plus V over R2 plus V over R3. Now my favorite part, cancel all the V. So you get 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So bear in mind, when the resistors are connected in parallel, it is 1 divided by the resistance plus 1 divided by the other resistance plus 1 divided by other resistance. You add up and then just invert it. Now, potential divider. So bear in mind, potential divider can only be used in series circuit. Why series circuit? Because current has only one path to flow. What if the circuit given is in parallel? Don't worry, just simplify it to become a series circuit. So this is the diagram of the potential divider. So series, yeah, these two resistors are being connected in series. I call this as R1, I call this as R2. Okay, this is a voltmeter, I connect to R2. So I call this as a V output voltage. This is called total voltage. Is that okay? Now, okay, the ratio, the formula, if you want to know. Formula, we don't use current because the current passing through R1 and R2 is the same current. So I don't compare current. I use the ratio, right? Potential divider is using the ratio. So I want to find the V output, V across R2 divided by the ratio, total voltage, which resistor is connected to V output is R2. So over R total. So V output modified over V total is equal to R2 over R1 plus R2 because R1 and R2 are being connected in series. This is the ratio if you want to know. Now, fuse, right? Fuse. Okay, I write down the symbol first. This is a symbol of the fuse, horizontal line cut through. Right, the function of the fuse. To protect electrical appliances. So, okay, you want to know how the fuse protect the electrical appliances? Let's say I have a fuse. Fuse come with a fuse rating. Inside the fuse, that is a thin wire. Let's say the fuse rating. Okay, what is fuse rating? Fuse rating means maximum current that is allowed to flow through the fuse. Okay, let's say the fuse rating of this fuse is 2 ampere. So this fuse only allows 2 ampere to flow through it. Let's say we have a current of 2.5 ampere. So if there's a current of 2.5 ampere, which is more than the fuse rating, what happened? This wire, the thin wire inside the fuse, will be melted and then cut off the circuit. Melted, right? It's like switch open and the whole circuit is being cut, right? So this fuse is committing suicide to save the electrical appliances. That is how it is protecting the electrical appliances. Now, we move on to magnetic field. The definition of magnetic field is a region in which a moving charge, remember, is about moving charge because current must flow in a conductor. Current must flow, meaning to say that the charge must move throughout the whole circuit. When a moving charge is placed in a region in which a moving charge experiences a force. Okay. Moving charge experiences a force when experiences a force. That's all. When placed in that region. Right? Magnetic field, okay, flows from north, okay, pole to south pole. Remember that. Okay, that's all is about magnetic field. Magnetic force, bear in mind, magnetic force arises due to interaction between two magnetic fields. Okay, for example, I draw. Let's say you have magnet, two magnet, opposite pole. So this is the magnetic field that flow from north to south, right? And then you have a current, carries the current from A to B. As long as there is a current flows through this conductor will have magnetic field around it. The interaction between these two magnetic fields gives rise to the magnetic force. And the direction of the magnetic force can be determined by using your Fleming's left-hand rule. Find my cat. F represents the direction of the force. First finger represents the direction of the magnetic field from north to south. Second finger represents the direction of the current from positive to negative. Okay? Fleming's left-hand rule and Fleming's right-hand rule. When to use this? For Fleming's left-hand rule, first of all, current must flows in conductor. There must be a current flows through the conductor. Got it? Fleming's normally used to find force. Used to find direction of force. Okay? Can be used in DC motor normally. Fleming's right-hand rule, right? No current in conductor. No current flows through the conductor. Normally used to find EMF induced or induced current. Direction of the induced current is the same as the direction of induced EMF. Right? Same thing. Find my cat, right hand. This is my right hand. North to south. Thumb represents the force, right? Or the motion. And then this second finger represents the direction of the induced EMF or the direction of the induced current or current induced. Normally used in generator, AC generator. Now, EMF induction states that, okay, the EMF EM inductions means electromagnetic induction. EMF means electromotive force, the voltage, right? Voltage induced is directly proportional to the change in magnetic field. As long as there's a change in the magnetic field, voltage or the current could be induced. That is electromagnetic induction. AC generator. So AC generator use slip rings, not split ring, sorry. Slip rings commutator. Slip rings commutator. Let me draw it. Okay, it's like this, north, south. And then I have a coil in between. I might not be good in drawing. I hope you don't mind. Okay, one is okay to this and the other one is to the other one. And then normally we connect to maybe a light bulb here to see whether the light bulb is lighting up. This is carbon brush. Okay, the function of the carbon brush is to act as the circuit completer to connect the slip rings and the light bulb or filament. You see, each and every side of the coil has its own ring. That is why you have two rings there, right? Graph of, okay, let me explain. Did I explain here? Okay, I will explain here later, yeah? How the current is being induced in the AC generator. Now I draw the graph for the AC generator. Okay, this is called slip rings. Yeah? Graph of the AC generator is like this, right? Okay, you need to know how to draw. Okay, output voltage or the induced voltage, yeah? Okay, this is the time. Okay, like that. Right, when the coil is in this position, right, it cuts maximum magnetic field. So it will induce maximum output voltage. Zero output voltage is when the coil is at vertical direction, up and down. The coil is at vertical direction because, right, in between the two sides of the coil is nothing. It's just air. So no cutting of magnetic field occur. Therefore, EMF cannot be induced. Let us see how the current or the PD is being induced in the coil. Okay, can I draw something first? This is a generator, right? It is the AC generator. But I want you to see here, first of all, okay, you just imagine that this is a magnetic field. Okay, North Pole. Okay, going into a solenoid or the coil. Same thing can be explained to the AC generator, yeah? Just bear in mind. And then I have V, voltmeter. So magnet has its own magnetic field. It's just that we cannot see. The magnetic field of the magnet is invisible. Remember that. So magnet has magnetic field that goes from N pole to South pole. And then when the magnet is inserted into the solenoid or the coil, right? So when magnet moves towards coil, magnetic field of magnet is being cut by coil, which causes a change in magnetic field. A change in magnetic field induces current, induces voltage or EMF in coil. That is why voltmeter deflects. Is that okay? Magnet has magnetic field and magnet moves towards coil. Magnetic field cut by coil, change in magnetic field. So a change in the magnetic field can induce the current or the PD, voltage. Now, transformer, this is transformer. Okay, Bear in mind, okay, the one that is being connected to AC supply is called primary coil. The one that is being connected to maybe voltmeter or bulb or lamp, this is called secondary coil, right? The core of the transformer is made of soft iron core. Why soft iron core? Because soft iron core is a magnetic material. It could, right? Because when you conduct the experiment in the air, some of the magnetic field that flow out from the primary coil could be, right, attracted to other magnetic fields nearby. So that is why soft iron attract back the magnetic field to make sure that the magnetic field from the primary coil will go to the secondary coil, right? But the coil is made from copper. Why? Because copper is a very good conductor. Copper has a very high conductivity, right? It can conduct electricity, less heat generated. Right? Now let me explain the working principle of the transformer. AC, okay, produces varying magnetic field. Okay? Okay. Varying magnetic field from primary coil is being cut by secondary coil, which causes a change in magnetic field. Therefore, EMF is induced in secondary coil. So if you talk about the light bulb will light up. So the formula for transformer, NS over NP is equal to VS over VP. Remember, NS is the number of coil in the secondary coil. Number of turns, right? In the secondary coil. NP is the number of turns in the primary coil. VS is the secondary voltage. VP is the primary voltage. So one more thing, if transformer, if the question mentioned transformer is 100% perfect, right? Efficient, then you do this. Okay, bear this in mind. Total input power of the transformer is equal to total output power. Total input power is I primary, V primary. Power is IV, yeah, VI. Is equal to total output, I secondary, V secondary. Yeah, current, secondary current, and secondary voltage. That's all. Now, alpha particle scattering experiment, there are three results that you have to explain. First one, most. Use the word, yeah, keywords. Most of alpha particles pass through gold foil, okay, undeflected. I will give the reason. These are just the result. I will give reason at the back, right? The second point, some of alpha particles were being deflected at angles, different angles. And the third result, a few alpha particles bounce back to original hub, right? So you have to talk about, okay, most, some, a few, right? So reason, let me give you the reason. Why most of the alpha particles just pass through undeflected, right? It is because atom is mostly empty space, right? There's nothing, this just vacuum, right? So that is why most of the alpha particles just pass through undeflected. Some of the alpha particles were being deflected at angles. Why? Because nucleus is positively charged. Okay, and okay, alpha particles are positively charged. Like charges repel. So when alpha particles come closer to nucleus, more, okay, deflection occur. The third one, okay, why a few alpha particles bounce back to original path? That means reflect back, right? It is because nucleus is very small and dense. You have to mention dense, yeah? Because alpha particle is a big particle, right? If the nucleus is less dense as compared to alpha particle, then the nucleus will be bounced off, right? Alpha particles that have head-on, head-to-head, head-on collision with nucleus, okay, were reflected at 180 degrees. Go back to their original path. Now, isotopes, this is a little bit like chemistry. Isotopes means the nuclides, okay, which have the same proton number but different neutron number or nucleon number is not a problem. And bear in mind, isotope exhibit the same chemical properties. Why? Because they have the same number of electrons. It is the number of electrons that gives rise to the chemical properties, that give the result to the chemical properties. But doesn't mean that the isotopes have the same physical properties. Maybe this isotope is solid. The other isotope of 8 is liquid. That is what we call physical property. Nuclear fusion and nuclear fission, right? Fusion means that, okay, two light nuclei combined to form a larger and more stable, okay, nucleus by releasing energy. Example, formation of stars, right? Nuclear fission, right? A heavy, unstable nucleus split into smaller fragments by releasing energy. Example, the one that we use in nuclear power station, right? To generate electricity. And the energy is quite promising. Now, alpha, beta, and gamma decay. Bear in mind, alpha is called helium nucleus. So 42He, if you remember, right? Alpha decay, that means, let's say AZX. A represents nucleon number, Z represents proton number. If this element, this nuclide, right, undergoes alpha decay, then you take the nucleon number minus 4. No division, sorry. Nucleon number A minus 4, Z minus 2, right? You form another element plus alpha. That's it, right? Beta is called fast-moving electron. Fast-moving electron, 0, -1, beta, right? So if this nuclide undergo beta minus 0, so you just put A here. Doesn't matter. A and then Z plus 1, yeah? This is Y plus 0, negative 1, beta. Because the nuclear number on the left-hand side must be balanced by the nuclear number on the right-hand side. The proton number on the left-hand side must be balanced by the proton numbers on the right-hand side, the sum of the proton numbers on the right-hand side. Gamma is called electromagnetic, okay, wave. So A, Z, X, okay, gamma, you still form the same one, but it's a different element due to the energy release. Oh, this is the symbol of gamma, by the way. Now, half-life definition is the time taken for a radioactive nuclide to decay to half of its original activity or original count rate, doesn't matter, or original number, right? It is, I need to see the time decay to half original value, right? The unit of half-life could be in second, in days, in years, in weeks, right? In minutes, hours, etc. It is the time. It is the unit of time. Okay, now let us move on to the last topic here, space physics, right? It is newly introduced in 2023. So planet, it is just like general knowledge. It is a large object orbiting a star, clearing its orbit and nearly spherical in shape. So when we do calculation of the orbit of the planet, we always assume it to be circular orbit, right? To simplify our calculation. Satellite, it is an object in orbit around a planet. It may be natural, like the natural satellite of Earth is Moon, or artificial GPS satellite, right? Asteroids and meteoroids are the rocky objects which are smaller than the planets, cannot be considered as a planet. And most of the asteroids are found in the asteroid belt between the orbits of Mars and Jupiter. So phases of the moon you have to memorize, right? Right, new moon, especially the ones that are highlighted, right? So here I'm using yellow color, new moon, right? New moon is when moon is between the sun and the earth. Full moon is when the earth, right, is between the sun and the moon. Memorize this, right? Waning, I think waxing crescent are more popular. Waxing crescent, memorize, right? Okay. So, and then waxing gibbous are also, okay. Uh, Waxing gibbous is also very popular, right? So, if you have time, might as well memorize all because we don't know whether they will give you third quarter, first quarter, waning crescent, waning gibbous, right? So might as well memorize all. But new moon and full moon are very, very important, right? So one light year, the definition is the distance that is being traveled by the light in 1 year. 1 year you have 365 days, remember, right? You have to convert to second. Right? How to convert to second? 1 day, 365 days. 1 day, you have 24 hours. 1 hour, 60 minutes, 1 minute, 60 seconds. Remember that if they want it in second. If the speed of light, okay? So it's given. Okay, normally we use, okay, speed of light is equal to distance over time. So 1 light year is distance, speed of light times time. Speed of light is normally 3 times 10 to the power 8 meter per second. So that is why you have to convert this. 24. Let me do it. 3 times 10 to the power 8 times 365 times 24 times. So 1 light year is about 9.46 times 10 to the power 15 meter. Now, life cycle of a star. So life cycle of a star, you have to consider whether this is a small star or medium-sized star like our sun, or this is a giant star or the super giant star, right? So if it is a small, medium-sized star like our sun, you have to talk about nebula. So what is nebula? Nebula is a cloud, right? A large cloud of dust and gas. right? So they come together due to the gravitational force, pulling them together, right? Over a certain period of time. Of course, it would take million years. It could form protostar. Protostar is like a large globe. You have a fixed shape already. The star has a fixed shape. The problem is that, okay, shape is not a problem. The problem is that there is no process of fusion occur in the protostar, right? So that is why, okay, that is protostar. And then keep on attracting, okay, because why no process of fusion occur in the protostar? Because the temperature and the pressure is not high enough. Temperature and the pressure are not high enough to carry out the process of fusion. So of course, okay, keep on attracting all the particles or the dust in the universe, eventually form a main sequence, or we call it a stable star. Main sequence can also be called stable star, right? Stable star, why it is called stable star? This is very important, right? Because the process of fusion, right? Fusion, remember, just now I define fusion. I say fusion give out a large amount of energy outwards, right? Outward pressure, outwards, okay? Pressure by fusion is balanced by inward pressure due to gravity, gravitational force. Right? In the process of fusion eventually runs out because the hydrogen is the one that carry out the process of fusion to form helium. But nothing lasts forever. Hydrogen eventually runs out. The process of fusion cannot occur. So that is why the only force that acts on the star after main sequence, right? It is the gravitational force. So this gravitational force, right, will pull the star inwards. So the gravitational force will pull the star inwards. The star becomes smaller, so get hotter. Now the process of fusion can occur. But due to the lack of hydrogen, the process of fusion will carry out by the other particles, such as helium, to form a larger element. Which we call it as red giant. And after red giant, the ending of the star, it would turn into white dwarf, right? So why we call it as white dwarf? Because it gives out a lot of light. Because if initially they are small size star, so eventually they become white dwarf, and then they will give out a lot of lights. That is why it is in terms of white. But eventually, once they run out of light, they will turn black. We call it as black dwarf, right? And okay, life cycle of a big or super massive star start from main sequence, form a red supergiant, right? Red supergiant is super, super large, and supernova will occur. Supernova is the explosion, right? Explosion of the big red giant, supergiant star that give out a large amount of energy across the universe, right? So the core of the supernova, after that, the core could form neutron star or black hole, depending on the size of the star initially. If it is super duper massive, then it will form black hole. Black hole has a very large gravitational force. Basically, if the light passing through it, it will be able to attract the light and nothing can escape from it. Yeah. So Hubble's law states that the speed at which the galaxy receding, that means galaxies are moving away, they're directly proportional to the distance between the galaxy and the Earth, right? Hubble constant is the constant of proportionality due to the Hubble's law. Hubble's law says the speed of the galaxy moving away is directly proportional to the distance between the galaxy and Earth, right? To get rid of this proportionality, put H naught, Hubble constant, right? Hubble constant will give you, Hubble constant is equal to speed of galaxy divided by the distance. So it gives the rate of expansion of the universe. Right, redshift is the increase in the wavelength. Red color has the longest wavelength, which is between 600 nanometer to 800 nanometer. So that is why you could see nighttime. You try this under the night sky. Look at the star. Wow, that's romantic, right? Look at the star. Do you see the color of the star is close to yellow color, orange color? That is close to red region, right? Because the stars are moving away from us. Redshift is one of the solid evidence to the Big Bang theory. So redshift is the increase in wavelength, shift towards the red end of the spectrum of light from the galaxies that are moving away from us. Right? They will give out light in terms of red color, indicating expansion of the universe, Big Bang Theory. Right? CMBR stands for cosmic microwave background radiation. So what is CMBR? CMBR is a weak radiation detected in all directions uniformly, right? It is actually considered leftover energy from the Big Bang. So it is the key evidence, right, for the Big Bang Theory as well. So explosions, supernova occur, give out radiation that is very uniform in all direction in terms of microwave region. Okay, so that is all about this final boost for your coming IGCSE Physics Paper 4. So bear in mind, you are ready to show the examiner. Tell yourself, I am not just ready, but I'm also so solid. Let's finish strong. You got this. If you found this useful, drop a like, subscribe for more physics help, and I see you in the next one. And good luck. Very, very best of luck in your coming IGCSE Physics Paper 4. Bye.